Pluto is a remote and enigmatic dwarf planet that was once part of our solar system's planetary group. However, recent surprising announcements by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight with a startling discovery. They proposed that this frigid world is on a potential collision trajectory with Neptune. But how could this occur, and what would be the repercussions of such a colossal event? Are we witnessing a rare astronomical phenomenon, or is there something more to this looming cosmic clash? Join us as we examine the possibilities of a Pluto-Neptune impact. Pluto, a former planet reclassified as a dwarf planet partly due to its unusual orbit, remains a subject of intrigue and research in the astronomical community. According to recent forecasts by leading scientists, Pluto's trajectory is dangerously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a possible perilous collision between these two bodies that could present a significant threat to Earth. How is such an event even plausible? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one complete revolution. But the fascination doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating notably from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually intersects Neptune's. The stability of Pluto's orbit amid these complexities is proof of the intricacy of space mechanics. The three-body problem in space involves figuring out how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how the paths of Neptune and the Sun's gravity all interact in a complex way. The terms libration and latitude libration, along with the VSK oscillation, are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a U-libration. In the context of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it's positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their paths from colliding. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VSK oscillation, named after three scientists, von Zippel, Kalou, and Lasker, who studied how things move in space. It's about how three space objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VSK oscillation helps us understand why its path around the Sun is so unusual. Even though Pluto's path seems erratic, this oscillation helps keep it moving smoothly over a long time. The VSK oscillation shows that even if things in space seem wild and random, some patterns and rules keep everything in order. All of these components help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or get thrown off course. This three-body problem helps us understand how these parts change because of the way these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, distant worlds, and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, effectively keeping the chaos at bay. Recent computer tests have helped us understand how the large planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune has a special connection with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's path steady. But Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in keeping Pluto's orbit safe and stable, and Saturn assists a bit too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for an extremely long time, even billions of years. So it's like Neptune, Jupiter, and Saturn are all working together to ensure Pluto keeps moving safely in space without encountering trouble. These phenomena are essential in the context of the universe for maintaining the order and predictability of space bodies' movements. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable paths, leading to a domino effect on other celestial bodies. For Pluto, especially with discussions about it possibly crashing into Neptune in the future, understanding its orbit is really important. This provides a clearer picture of the solar system's dynamic nature. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is vividly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using computer simulations has been extremely useful for scientists to figure out how Pluto moves in space. These simulations use complex math to replicate how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even minor adjustments can make a big difference in where Pluto goes. Back in the late 1980s, these simulations revealed something really interesting about Pluto's path. Even though it has factors like U-libration and latitude libration to keep it steady, its orbit can still be quite wild and unpredictable. If you start off with just a tiny difference in where Pluto is or how fast it's moving over many years, its path can end up looking really different. But even with all this chaos, Pluto's orbit stays stable for an extremely long time, like billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting cosmic events, especially when they involve chaotic orbits like Pluto's, poses significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainties. While numeric simulations provide a powerful means to understand and anticipate the future paths of celestial bodies, they also highlight the limitations in our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor error or oversimplification can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto reminds us how our knowledge about the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching effects, influencing the stability and trajectory of other bodies within the system. So why are major astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complex forces trying to keep such an event from occurring? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing astronomy, provides a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in the reclassification of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's stance on Pluto's reclassification is rooted in the ever-expanding knowledge of our solar system. He views the reclassification not as a demotion but as a necessary adaptation to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits, such as Pluto's, as a reminder of how much there is still to discover in space. The fascination with these unknowns, especially the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, leading to further exploration and discovery. However, this is not a concern, as Tyson reminds us of the importance of ongoing research in refining our understanding of space. As our understanding of the solar system deepens, the lines between scientific knowledge and public curiosity often blur. The excitement surrounding potential celestial events, such as a hypothetical Pluto-Neptune collision, showcases the public's fascination with space. In popular media, science fiction has often taken the concept of orbital chaos to extremes, presenting scenarios where minor changes lead to catastrophic outcomes. However, Tyson's views emphasize the importance of balancing scientific accuracy with the wonder and excitement that space exploration brings. Tyson acknowledges the allure of these what-if scenarios but stresses the need for rigorous scientific inquiry to guide our understanding of space. Kaku, another major astrophysicist, has also expressed his ideas about the future of space exploration and the possible collision between Pluto and Neptune. Known for his expertise in theoretical physics, Michio Kaku has a reputation for making complex scientific concepts accessible to the public. In his discussions about space exploration and the potential collision between Pluto and Neptune, Kaku often focuses on the broader implications of such events. Kaku's perspective is shaped by his belief that humanity must become a multiplanetary species to ensure its long-term survival. He often discusses how studying celestial phenomena, like a potential Pluto-Neptune collision, could provide essential insights into the dynamics of our solar system and the risks we may face. Kaku is particularly interested in how advanced civilizations might deal with such cosmic threats. His work emphasizes the importance of technological advancements and space exploration as tools for understanding and mitigating these risks. Kaku also explores the idea of using advanced technologies to predict and prevent catastrophic celestial events. He speculates that with the right technology, humanity could potentially alter the course of celestial bodies to avoid collisions or harness their energy for beneficial purposes. In the case of Pluto and Neptune, Kaku suggests that while a collision is unlikely, studying the forces at play could help us develop strategies to protect Earth from future threats. He envisions a future where humanity has the capability to not only explore distant worlds but also to manage and manipulate the dynamics of our solar system. Kaku's views also extend to the ethical implications of space exploration and planetary defense. He raises questions about the responsibilities that come with advanced spacefaring capabilities and the potential consequences of altering celestial mechanics. His work encourages a forward-thinking approach to space exploration, where scientific discovery is paired with ethical considerations and a focus on the long-term survival of humanity. Both Tyson and Kaku's views on Pluto and Neptune reflect a blend of scientific curiosity and concern for the future. While they acknowledge the unlikely nature of a collision between the two bodies, they also recognize the importance of understanding the complexities of our solar system. Their perspectives remind us that space exploration is not just about answering questions but also about preparing for the unknown. As we continue to study celestial mechanics and the potential interactions between distant worlds, we must remain vigilant and open to new discoveries, ready to adapt our understanding of the universe. In conclusion, the remarkable phenomenon of Pluto's orbit brings attention to the delicate balance that governs our solar system. While the announcement of a potential collision with Neptune may initially seem alarming, the intricate interplay of gravitational forces, orbital mechanics, and long-term stability offers reassurance that such an event is unlikely to occur within our lifetimes. Neil deGrasse Tyson's emphasis on the importance of ongoing research and Michio Kaku's forward-thinking approach to space exploration underscore the need to continue studying these celestial bodies and their interactions. As we explore the depths of space and uncover its mysteries, we are reminded of the vastness of our universe and the remarkable mechanisms that keep it in motion. While the prospect of a Pluto-Neptune collision may capture our imagination, it also serves as a testament to the power of scientific inquiry and the resilience of our cosmic neighborhood.